there's no question that large-scale climate engineering is untested and dangerous. We've mostly thought about sulfur, and there's a lot of good reasons to think about sulfur because sulfur is what nature does, and there are very good reasons to think we would like to start very slowly if we ever wanted to do this and do something that was an analog to nature because we have some idea what the downsides of what nature does are. Nevertheless, there might be some good reasons to think about alumina. It turns out, first of all, there's been a lot of work on the environmental consequences of alumina in the stratosphere because it's in shuttle exhausts. There's a bunch of papers that look at the radiative and ozone-destroying properties of alumina in the stratosphere, and those make you think it might be useful. The big deal really is that alumina has 4 times the volumetric radiative forcing for small particles as does sulfur, and that means you have 4 times less surface area for the same radiative forcing, and this is a much bigger deal. You have roughly 16 times less the coagulation rate, and that's the thing that really drives removal. So you could get away, we think, with much smaller mass fluxes, but we haven't run those studies yet, so that might be wrong. The little picture is from a nanofabrication study, which shows you can make very high quality, and do this in just a jet in a very simple way, make high quality alumina particles just by spraying alumina vapor out, which oxidizes. So it's certainly in principle possible to do that. There's a big literature that's already looked at that. Look at the alumina or sulfuric acid functions, which are the mass-specific backscatter, so a measure of radiative forcing, and in fact I have it in watts per square meter per megaton. And those things fall off as the particles get larger. But even more important, the fall speed rises quite rapidly in this regime. And so as particles stick together and get large, they fall out of the stratosphere very quickly. And so particles that are too large are much less effective per unit mass.
If I could just clarify, so 10 megatons of aluminum dumped into the atmosphere would have no human health impact.
So let me be more careful here. Work to separate out the toxicological, so the alumina we've only begun to research and publish nothing. We haven't done anything serious on alumina, and so there could be something terrible that we'll find tomorrow we haven't looked at. Aerosol geoengineering looks like it is so cheap that the cost is basically not going to be an issue. That means that implementation decisions will be risk-to-risk decisions. The risk of doing it against the risk of not doing it. And it makes the problem of how we govern it fundamentally harder and different and novel. Another reason why I think more knowledge is good is I think this will turn out to be more complicated and harder to do than we now think. So I've told you that it's cheap to deliver materials to the stratosphere, and I'm convinced that's true. I don't think that will change. But I think the more we do research, the less easy this will look, the more complicated the environmental effects will look, and that's a good thing, because right now it looks too easy. So I think that if we do more research, we're likely to find out that it's harder and more complicated than we thought, and that the side effects are harder to manage, and that's a healthy outcome that will make it easier to do the management. It's an empirical question, how people will actually react to knowledge about this. Another reaction is to say, if these crazy scientists are so concerned about putting CO2 in the atmosphere, they want to think about these things, then that might actually mean we should be more serious about the risks of CO2 in the atmosphere. And by the way, it's not really a moral hazard, it's more like free riding on our grandkids. And by the way, it's not really a moral hazard, it's more like free riding on our grandkids.
It's more like free riding on our grandkids.